All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Victor Lee. He is VP of AI and ML at TigerGraph. Please join me in welcoming him to our virtual stage.
Thank you. It's exciting to be here. So I'm here today to talk to you about graph data science and machine learning for better healthcare outcomes. So the healthcare industry is massive, amounting to 17% of GDP in the US, with so much at stake, both in as far as economic and human well-being. Both private industry and the government are applying data science to try to maximize the benefits. But there are several challenges. The Brookings Institute has identified 4 challenges. The first being disconnected data, then privacy concerns, conflict with traditional decision-making, and misaligned incentives. The latter 2 are really policy issues, which we won't get into, but the first 2 are data and data science issues. So in particular, we're going to look at that disconnected data, and we believe that graph and graph data science is the solution to that problem. So Gartner has said that by 2025, graph technologies will be used in 80% of data and analytics innovations. So it's not a question of whether to use graph or not, you will use graph. But what do we mean by graph? Well, we're not talking about charts and figures. We're talking about this data model of representing objects as nodes or vertices, and then the relationships between them called edges, where those relationships are actually another type of data, and you analyze both the objects and the relationships. This is a very natural storage model because it tends to be the way that people think, and it's natural for representing transactions because that's just some activity between 2 entities. But if you think about it, data analysis is about taking relationships you know about and trying to infer additional relationships, or trying to see the pattern of relationships or correlations. So having relationship-based analysis is actually the most natural way to do data analysis. It takes a little bit of getting used to, but once you do it, you realize you're getting new insights. So it's excellent for breaking down those data silos where you have your different organizations, the clinical, the prescription, the genomics, all have their separate data in different formats. What you need to do is break down those silos and integrate into one centralized data set, which from that, you'll be able to see the big picture. You'll be able to see, connect the dots. And that those expressions we use about connecting the dots are really talking about the power of graph. So now you've got graph data. What about graph data science and machine learning? So first of all, it's giving you so-called richer, smarter data because you're breaking down the silos and you're representing knowledge through this graph structure. You're then able to ask deeper and smarter questions because you can ask questions about, do you see this pattern? Is this pattern frequent? You can follow several levels of relationship. In a traditional relational database, joining tables is an expensive operation. You may only be able to join 2, maybe 3 tables before you run out of oomph in your database. With a graph, because it's designed to follow relationships, going 5 levels, 10 levels deep, if you have the right graph platform, is very plausible. You also get these new computational methods, graph algorithms and graph enhanced machine learning, which is what I'm going to be talking about. And also because these patterns of interconnection have semantic meaning, such as saying this physician has treated this patient, this physician is affiliated with that office. When you pose questions and get answers in terms of these relationships, they're very understandable to humans. Some of the benefits, some of the real world outcomes we're seeing. We have healthcare providers and insurance companies who are able to represent their knowledge as large graph brains, and from that make better healthcare recommendations, which both improves the care and lowers the cost. We have supply chain optimization. This was in a different industry, but one manufacturer was able to lower their analysis of trying to optimize the supply chain from weeks, 3 weeks, down to 45 minutes. They're saving $100 million a year Healthcare could do the same. And it's excellent for, graph is excellent when you need to dig down and have human investigators actually look at the data. These first two, the graph analysis is happening under the hood, but in this last case, you may want people to actually look at the graph. So in the rest of my talk, I'm going to be talking about 3 ways that graph data science improves machine learning. The first is with unsupervised learning via graph algorithms. Second, providing more accurate models through using graph data features. And the third is graph neural networks and embeddings. And these 3 are all covered in more detail in a book called Graph-Powered Analytics and Machine Learning with TigerGraph that is available as free as an early release from O'Reilly. The first method I said was using graph algorithms. And there are many types of graph algorithms. I've shown 6 here. You may have heard of shortest path. You may have heard of community detection or finding clusters. Excuse me. But there are also algorithms for similarity, centrality, connectivity. Now, what can these do for you? These are all derived from math theory, but let's look at a real case. So let's say you're trying to find the most influential healthcare provider in a community. Why would you want to do that? Well, just like in social influence, in business and technological and in professional influence, this can matter. So say you're trying to introduce a new treatment, a new drug. If you can get that influential provider to adopt it, it's going to have a trickle-down effect. So how do you find who's the most influential? Well, you run the PageRank algorithm, which is designed to find influence within a network. And then who are they influencing? You run a community detection algorithm. So 2 different graph algorithms help solve this problem of finding who is the most influential and who are they influencing. Here's another use case of trying to recommend courses of action. You can think of the care that a patient has received as a timeline and different types of activity. And this is a dashboard where it shows that certain, negative warning signs have occurred. And so we want to take some intervention with this patient. And once we realize, okay, that intervention is necessary, we want to do a search of our database to see what similar, who has a similar situation. And you would simply click this button to identify those similar patients. Well, how does that analysis actually occur? You might be surprised to learn that this is modeled after what a company is really doing. They're modeling their data as a graph. So each of these orange nodes represents a person, and each of those actions, events that occur during the timeline is another type of node. So there are 2 types of nodes, person nodes and event or activity nodes. And the reason why they do it as a graph is to keep it flexible, because over time, more and more actions, activities are going to occur. Now, they're not just 2 persons. There are literally millions of persons in this database. So you have millions of persons, tens or hundreds of millions of these events. We have these connections. What you do is you find similar persons who have had similar situations by counting how many similarities, relatively speaking, do they have in these features, so-called. And it's not just 2 persons. So this analysis is relatively straightforward, but you have to compute it so many times that you want a platform that does parallel computation very well. And there are graph databases that specialize in this sort of parallel computation. The second way that graph can help is providing more accurate models, which gives you better machine learning training. Here's an outline of a machine learning pipeline. You start with getting your data, preparing your data, then you do something called feature extraction and selection, and finally you get to model training. And this is the state where most people think of, okay, now you're running your machine learning to try to develop the model for making predictions, and then this is lastly where you apply it to make specific predictions. But this step should not be ignored. This is where you're trying to enrich your data. If you look at this, represents a table of data. Each row is one object or entity of interest, And each column is what machine learning scientists calls a feature. If you have so many features, you can get a certain quality of predictive model out of it. The more and more informative features you have, the better model you're going to get. How do you get more and more informative features? By applying graph analytics. PageRank is considered a feature. Community membership is considered a feature. And let's look at an example. So at this example, we are looking at a prescriber of drugs and its connectivity to patients, to claims he's filed, to ICD codes, to pharmacies. We can extract patterns of features to see if who do they connect to and in what frequency patterns. So what ICD codes are occurring? Are they frequent? What is the average cost of medications? Is there affiliation with sort of routine or unusual facilities or prescription fillers? And so we actually have an example where a company extracted over 100 of these graph-based, relationship-based features, and they trained a machine learning model to predict whether this was sort of normal, easily approved behavior, or this behavior by the doctor was suspicious. And so it amounts to being a fraud detection system through graph patterns. The third way is using these new graph-based machine learning techniques, graph embeddings and graph neural networks. Some of the names that you will hear are algorithms called node-to-vec and deep walk for embeddings, graph convolutional neural network, graph recurrent network, and graph attention network. The first way, a graph embedding transforms a graph and looks at the pattern of relationships and summarizes it into a table, but where the columns in the table are so-called hidden or latent features. They are not things that a human would be able to observe here, but by applying analysis, mathematical statistical techniques to the entire graph as a whole, it comes up with a new set of features. And these features are such that so this now represents a numeric vector. Two vectors that have similar values are going to represent similar vertices in the graph. So we have a similarity measure. And once you have similarity, you can do things like recommendation. You can do classification and clustering. So that's similarity is one of the most important properties you can know because it enables so many interesting use cases. So by compressing the data, it becomes more scalable. You can handle larger amounts of data. And it's also transformed it into tabular format. And while it was really important that we had the graph here while we were extracting features, developing the graph structure. So knowing the graph structure itself is informative, but then we transform it into this latent table, which makes it compatible with traditional machine learning techniques. So you start with the graph, but then transform it, get the similarity measure, and enable traditional methods of analysis. That's great. But the real cool innovation is graph neural networks, where we don't do the transform, we leave it as a graph. So you start with neural networks. This powerful technique, deep learning, just means you have a neural network that is several layers deep. This one is 2 layers deep, but deep learning might mean 5 or more levels deep. That's deep learning. Graph, you get insight from connected data, from those graph algorithms, from just, as I said, just knowing that neighbors exist means things are closely related, closely similar. If you combine the two so that you are actually using the graph structure during the training process, you get the benefits of the added insight of connected data from modeling combined with the modeling power of neural networks. So those are graph convolutional neural networks and their related cousins, GRNs and GATs. To summarize, I have this outline of these things we've talked about. The graph structure itself gives you integrated knowledge in a very natural way, breaking down silos. You're able to ask deeper questions and ask questions that have very natural semantic meaning. And then we have these three ways that graph data science improves machine learning: through graph algorithms, which provide a toolkit for analytics and unsupervised learning; graph features, which characterize the data patterns based on patterns of connectivity, provides higher quality training data; and lastly, these graph-based machine learning methods themselves, graph embedding and graph neural networks. So I want to thank you very much for your time. It's been great speaking at AI4.
Wow, Victor, thank you so much. That was amazing. And I know this virtual audience is going wild with virtual applause. Thank you for sharing with us today. And for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our awesome exhibits. Thanks so much, and we'll see you around.